how does he actually solve these equations and see how the method plays out in the examples, especially for polynomials of degree 4, 5, and 6.
Right. And the source, it really centers on introducing and then applying a specific technique. It calls it the discriminant formula of Mourad Sultan Ezouidi Hism.
Okay.
Yeah, and the paper uses this formula as the key tool. It connects the polynomial's original coefficients to a new set of derived coefficients, and that ultimately leads to finding the roots.
Interesting.
And you'll also notice this specific phrase, Mourad Sultan LCHQKKP, it pops up quite a bit in the document, often right next to the formulas.
Oh. Okay, so the basics then. We're starting with a polynomial px set equal to 0, right? P equal. And the classic goal, find the values of x that make that equation true, the roots.
The roots, exactly.
And the source writes the polynomials in that standard form we all learned. Xn minus the first coefficient times xn1 plus the next coefficient times xn2 and so on. It uses LQ for these original known coefficients.
That's right. Those are the starting point, the LQs. And the central idea this document presents is, well, a method to figure out a new set of values. It calls these the SQ coefficients, and they're determined directly from those initial LQ values.
Okay, so you transform the L's into S's.
Pretty much. And the paper gives specific formulas to make that connection happen.
And that connection, you said, hinges on this discriminant formula of Mourad Sultan Ezouidi Hism.
Exactly.
There's a specific summation formula shown repeatedly. Now, reading complex math notation isn't great for audio.
No, definitely not.
Can you just describe what this formula does conceptually?
Absolutely. Think of it like a rule or maybe a set of equations. It takes the polynomial's original LQ coefficients, the ones you start with, and it transforms them mathematically into these new Sich coefficients.
How does it do that?
Well, the source applies this formula again and again, plugging in different values for an index, k. So k0, k1, k2, etc. Each value of k gives you a new equation that links the L's and S's together.
Okay, so you use this formula maybe multiple times to get a system of equations. These equations relate the known LQs to the unknown LQs. Then what? What does the paper show you do next?
Right. So once you have that system, the document then demonstrates a process it calls exact work.
Exact work. Sounds intense.
It likely involves some careful algebra, basically solving that system of equations you got from the discriminant formula. The goal is to find the specific numerical values for each of the skew coefficients.
Okay.
And what's really fascinating, and this is highlighted in the examples, is that often after this exact work, most of those skew coefficients, they just turn out to be 0.
Oh, interesting. Most of them. Why is that significant?
Well, think about it. If most of the SCOI values are 0, the whole structure of the problem simplifies a lot. The original polynomial equation, which might have looked really messy, can often be related back to a much simpler form. Sometimes it's as simple as like xn plus or minus some SCOI value equals 0, where that SCOI is the only non-zero one.
Right, and solving xn equals constant is much easier.
Exactly. Finding the roots of those simplified equations becomes way more direct, even for higher degrees like 4, 5, or 6.
I see. So the transformation using the discriminant formula and then finding the SQs, it's like a clever trick to strip away the complexity.
That's a great way to put it. It strips away complexity from the original equation, making the roots easier to grab onto.
That makes them easier to find.
Precisely. And the source then provides the specific formulas you need to actually calculate the roots using these simplified x-squared values.
Okay, let's make this concrete. Let's look at how this actually plays out in the examples from the source. It walks through several, right?
It does, yeah. The paper shows quite a few instances across different polynomial degrees. So for a degree 5 polynomial, for instance, written in that standard form with the LQ coefficients, the process involves applying that discriminant formula, doing the exact work to find the sus values, and then showing in the specific examples that most of those Qs are 0.
Okay, give us one.
Right. One example given is a degree 5 case where, after going through the whole process, all the cis values are 0 except for S3Q, and that S3Q equals 3.
S3, okay.
Yeah. And the document then provides a direct formula for the roots, which are labeled SK in this instance. And that formula involves the fourth root of that non-zero S3Q value. so the fourth root of 3,
Uh-huh.
combined with complex exponentials.
Okay, complex numbers are showing up.
They are. And another degree 5 case in the paper shows a similar thing, but
Yeah.
this time S3Q equals 325, and all the other skews are 0.
325.
Right. And the roots are calculated using the fourth root of 3125, which the paper shows is 5 times the fourth root of 5. And again, those complex exponentials.
They argue.
And there's a third degree 5 example where S4Q is the only non-zero term. It's equals negative 3125.
Negative this time.
Negative. And here the roots use the fifth root of negative 31425. The calculation leads to roots expressed using the number 35 times a complex exponential.
Complex exponentials?
Yeah.
You mean like e raised to the power of IO times some angle?
Exactly that. Those e to the I theta terms are absolutely crucial.
Why are they so important here?
Because they capture the rotational aspect of roots in the complex plane, especially when you're dealing with roots of negative numbers or finding all the different roots, like the nth roots of unity.
Right.
Which often pop up in those simplified equations like xn equals constant. The complex exponential gives you the direction or the angle of the root.
Gotcha. And the paper applies this whole method to other degrees too, not just degree 5.
Oh, yeah. It explicitly includes examples for degree 4 polynomials as well, and it follows the exact same steps. Determine the initial LQs, use the discriminant formula, find the SQs.
Expecting most to be 0.
Right. And then provide the root formulas. For degree 4, the roots are labeled ek. And the formulas involve those non-zero issues, usually the original L0Q coefficient 2, and you guessed it.
Complex exponentials.
Complex exponentials. For instance, there's a degree 4 example, px equals by 4, 60 by 3 plus 6. And the roots are given in the form equals 12 plus 12 times a complex exponential.
So it's constant plus a term with a complex exponential.
In that case, yes. And the document also briefly touches on degree 6 polynomials.
Degree 6, okay.
Again, same process. Find xq values from the LQs, then provide root formulas using the xqs, L0q, and complex exponentials. One degree 6 example gives roots looking like 11 plus 3 times the cubic root of 1332 times the complex exponential.
Wow. So the pattern seems really consistent across degrees 4, 5, and 6 in this source document. You transform the polynomial using that special discriminant formula to get these Q coefficients. You often find a simplification where most does become 0.
Yeah, that seems key.
And then you use specific derived formulas involving the non-zero Qs and complex numbers to actually calculate the roots.
That sums up the method exactly as it's applied step by step throughout all the examples shown in the document. The key result for each polynomial they show is that final explicit formula for its roots, and it consistently brings in complex exponentials.
Okay, let's quickly recap the path then.
Sure.
Just trace the steps Ezouidi lays out in this document for finding polynomial roots using this specific method.
Okay. Yeah, it really seems to boil down to 4 main steps based on what's presented in the source.
Step 1, you start with your polynomial equation, px equals O0, and you know its coefficients, the LQ values.
Right, those are your givens, your starting numbers.
Step 2, you apply the core tool, the discriminant formula of Mourad, Sultan, Ezouidi, Jessim. You use this formula, maybe plugging in different index values like Ka, Z, 0, 1, 2, to create a system of equations. And these equations connect the LQ coefficients to the S coefficients.
Yep, that's the transformation step, moving from one way of looking at the polynomial structure to another using that specific formula.
Step 3, you perform what the paper calls exact work.
The heavy lifting.
Right. This is the algebra part, solving that system of equations to figure out the actual numerical values for each of the set coefficients. And like we said, this step often reveals that most of those that takes are just 0.
Correct. That simplification seems to be a really important outcome of applying this specific process.
And finally, step 4, you take the resulting set values, especially the 1 or maybe 2 that are non-zero, and you plug them into specific derived formulas that are provided right there in the document. And those formulas then directly give you the roots of the polynomial, the SKKK, SK values. And these root formulas consistently involve complex numbers.
That 4-step sequence really captures it. Start with L's, apply the formula, solve for S, finding the non-zero ones, and then use those S in the final root formulas. That's the framework demonstrated again and again across the examples in the paper for degrees 4, 5, and 6.
Well, that was certainly a deep dive into a very specific, very intricate method for solving higher degree polynomials. It's quite remarkable, really, to see such an explicit step-by-step process laid out like that in this document.
It really is. The focus on that one particular discriminant formula and its systematic application, that's very clear. And coupled with the consistent appearance of complex numbers in the final root expressions, that's what really defines the approach presented here.
Yeah, and seeing those complex numbers pop up so reliably in these solutions, it just underscores how they aren't just some abstract mathematical oddity, are they?
Not at all.
They seem essential components when you're actually trying to find all the roots of polynomials, especially once you get past the simpler quadratics.
Absolutely.
And that phrase again, Mourad, Sultan, K appearing with the formula, it just reinforces that feeling that this is a very particular, very documented system being presented.
It definitely highlights the fundamental nature of the complex plane. The idea that it contains all the polynomial roots, that's the fundamental theorem of algebra, right?
Right.
This method, as it's shown in the paper, provides one specific pathway to explicitly finding those roots, navigating through that transformation of coefficients.
Absolutely. And for you listening, maybe this deep dive into Ezouidi's method has given you a glimpse into the, well, sometimes surprising ways mathematicians tackle problems, transforming one set of information into another to reveal hidden solutions. It's pretty neat.
It is.
So, what does this all mean in the end? We've explored one very detailed method for tackling a classic challenge, finding polynomial roots. It's a problem with centuries of history.
A very rich history.
And seeing this makes you wonder, doesn't it, about the vast, intricate landscape of mathematics out there. What other unique formulas, maybe other kinds of transformations or hidden connections are still waiting to be discovered? Connections that might simplify problems we currently think are just intractable.
That's a great thought.
Keep that curiosity alive.